So, we have seen how to use the projection operators to construct symmetry adapted linear combinations for one dimensional and two dimensional representations. For one dimensional representations, the method of constructing is very easy because the characters are the same as the matrix elements. Since it's a one dimensional matrix which is simply a scalar, instead of using the characters of the instead of using the matrix elements, we can directly use the characters. For two dimensional irreducible representations, okay, the characters, if you use the characters, you have less information than using all the matrix elements. So, a character of a two dimensional matrix just gives is just one number, whereas a 2 by 2 matrix has 4 numbers. So, if you use the characters, then what you construct are things called incomplete projection operators, but with a little bit of manipulation, you can use the incomplete projection operators to construct appropriate symmetry adapted linear combinations. Okay. Now, this method of using the incomplete projection operators is more efficient because if you have the character table in front of you, you can immediately construct it. Okay. Now, let us try to see what happens when you have 3-dimensional irreducible representations, okay. And we will try to construct symmetry adapted linear combinations for 3-dimensional irreducible representations. Okay. Now, once again I want to remind you that the irreducible representations can either be 1-dimensional, 2-dimensional or 3-dimensional, and most of the groups have only 1-dimensional or 2-dimensional irreducible representation. If you look at the character tables of various groups, you will find that there are very few groups that have 3-dimensional irreducible representations, and they correspond to the very big groups like tetrahedral and octahedral and various variants of those. Okay. One such group is the octahedral group that has an irreducible representation which is 3-dimensional, and we will see how to construct a suitable basis for this 3-dimensional representation. Okay. So, let us the statement of the problem we will do is for an AB6, and AB6, what I mean is octahedral AB6 molecule, find the basis for a 3-dimensional irreducible representation starting with the 6 sigma orbitals on A. So, the A atom is bonded by 6 sigma orbitals. Okay. So 4 are in this plane and 2 are in the plane of the board. So, you have these 6 sigma orbitals going from A to the B to the 6 B atoms. So, starting with these 6 sigma orbitals, let us go through the procedure and construct the symmetry adapted linear combination, and what we will get is a basis for a 3-dimensional irreducible representation. Now, the first thing you will ask is which 3-dimensional irreducible representation will you get a basis for, and to do that, what we have to do is to start with the 6 sigma orbitals. So, you have sigma 1, sigma 2, sigma 3, sigma 4, sigma 5, sigma 6. Okay. So, these are bases for a 6-dimensional representation. Okay. These form the basis for a 6-dimensional representation, and since it is a 6-dimensional representation, it will be reducible. It cannot be an irreducible representation. And then so let us go ahead and calculate the characters of this reducible representation. Okay. So, in order to find the character of any element of any class in this reducible representation, what you need to do is to operate on this vector sigma 1, sigma 2, sigma 3, sigma 4, sigma 5, sigma 6, okay, by the various operations of the group, and then find out the characters of each of them. Okay. Now, the octahedral group, this molecule belongs to the octahedral group, octahedral point group OH. The order of this group is 48. So, there is 1 plus 8, 9, 15, 21, 24, and then there is another 24. So, there are 48. So, the order of this group is 48, okay, and it has 10 classes. The 10 classes are identity C3, C2. So, there are 8 C3 operations, and they all fall in one class, there are 6 C2 operations that fall in another class. There are 6 C4 operations, C4 and C4 cube actually, which fall in a class. There are 3 C2s which are basically C4 square. So corresponding to the C4 axis, the C4 axis also acts as a C2 axis, but these two operations fall in different classes. There is an inversion. Octahedral molecule has a center of inversion. The 6 C4 axis, the 6 C4 operations also give rise to 6 S4. Then the 8 C3 gives rise to 8 S6. In addition, there is 3 sigma H and 3 sigma D, okay? And 6 sigma D. So these are the 48 operations, and these are the 10 classes. And since there are 10 classes, there are 10 irreducible representations, and the dimensionality of them are, there are 1, 2, 3, 4. So 4 one-dimensional representations, 1 and 1, 2 two-dimensional representations, and 1, 2, 3, 4 three-dimensional representations. So T's are the three-dimensional representations, three-dimensional irreducible representations. Now I'm just showing some of the characters, and we'll come to this in a bit. Okay, these now when we look at this, the 6 sigma orbitals, sigma 1, sigma 2, sigma 3, sigma 4, sigma 5, and sigma 6, they form the basis for a 6-dimensional representation, and clearly a 6-dimensional representation has to be irreducible. Okay, so we can work out the characters of various classes in this reducible representation. For example, if you operate by C3 on this vector sigma 1, sigma 2, sigma 3, sigma 4, sigma 5, sigma 6, what you will get is sigma 1 when you operate by C3, and you can think of C3 as going diagonally in this direction. Okay, so then sigma 1, it takes it to sigma 4, or it takes it to sigma 5, and so on. You can work out all the what happens to the remaining. So then sigma 2 is taken to sigma 6. Okay, sigma 3 is taken to sigma 1, sigma 4 is taken to sigma 2, and so on. Okay, so these C3 operations, they cause they can be represented, their action can be represented by this matrix, and so this is a matrix corresponding to C3, okay, in this 6-dimensional reducible representation. And once you have this, you can easily work out the character of C3. So the character of C3 is 0, because everywhere along the diagonals you have 0. Character of identity will be 6, because you have 1 along the diagonals. Identity will just leave all of them the same. So you just have 1 along the diagonals and you have zeros everywhere else. So the character of identity will be the dimensionality of the representation, that is 6. Character of C3 is 0. Similarly, you can show character of C2 is 0, character of this C4 square. So there are two kinds of C2s. There are C2s like this axis will be a C2 axis, and so you will have 6 such C2 axis. In addition, you will have 3 axes. The C4 axis corresponding to each of these will also be a C2 axis, and so these have characters of 2. The character of this is 2, because if you imagine C4 operating on sigma 1 will leave it unchanged, will not change sigma 1. Okay, C4 operating on but it will not change sigma 1 and sigma 2. Okay, so these two will have 1. Okay, but it will take for example, it takes sigma 5 to sigma 4, sigma 4 to sigma 6, and so on. Okay, so these two will have 1 along the diagonals, everything else will have 0 along the diagonals. So the character of that is 2. Similarly, the character of C4 will also be 2. Okay, and you can work out the character of inversion will be 1, because sigma 1 will be taken to sigma 6. No sigma orbital will be left unchanged. Okay, similarly S4 is 0, S6 is 0, sigma H the character, it will leave 4 out of 6 of the sigmas will be left unchanged. So, the character of sigma h is 4 and character of sigma d is 2. Okay. So, these are the characters corresponding to the reducible representations, and once you have characters corresponding to the reducible representations, you can decompose this into set of irreducible representations. So, you use your usual method of taking the characters of this reducible representation and calculating how many times each irreducible representation appears in this representation, and if you do that, you will get that this reducible representation can be written as a sum of A1g, EG and T1u. Okay, so it is a 6-dimensional representation. A1g is 1-dimensional, EG is 2-dimensional and T1u is 3-dimensional. So, it is a sum of these 3 representations, and you have to work it out. You can easily verify this. For example, if you look at the character of C4. So, the character of C4, if I add all these characters, I get 2, which is the same as 2 here. Okay. So, you can verify using the character table that this is indeed a valid decomposition of this representation. Okay. So, now you have one dimensional representation, a 2-dimensional representation, and this is the 3-dimensional representation. So, this is the 3D irreducible representation, and what you want to do is to construct appropriate linear combinations of the sigmas such that they become a basis for T1u. Okay. So, we want to find appropriate basis for T1u using sigma. Okay. So, what we are going to do is to find the appropriate symmetry adapted linear combinations of sigma 1 to sigma 6, okay, such that they form a basis for T1u. Okay. And this exercise, since we have the characters of all the operations, okay, all we need to know is we can construct the projection operators. Okay. And in order to construct the projection operators, you need to know how each of these operations acts on the sigmas. Okay. So let us start. We look at the projection operator of T1u, projection onto this irreducible representation onto T1u of and this projection operator, projection of sigma 1. Let's look at the operation on sigma 1. So, this is the incomplete projection operator, incomplete projection operator onto T1u. Okay, so, it is a projection onto T1u. Okay, and this acting on sigma 1, this can be written as sum over all R, okay, and it will be chi in T1u of R times R acting on sigma 1. Okay, so the various operations, you look at their, you see what they give as a result of that operation and how it operates, and multiply it by the characters. Okay. So now if you look at chi R, these are the characters of the various operations. Okay. Now this sum is over all 48 operations. Okay, so you have to take the sum over all 48 operations. Okay, now that seems very tedious, but things will become a lot easier once you see that some of them are 0. So, you do not need to consider this here you have 8 here and another 8 here, which are 0. Okay, so, you do not need to worry about those 16, but still you have the remaining 32 that you have to consider. Okay, and let us go ahead and work it out. So we need to know what happens when various operations act on sigma 1. Okay, so let's first look at the identity. Identity, and sorry, this should be multiplied by 3 by 48. Okay, 3 is the dimensionality of T1U. T1U is a 3-dimensional irreducible representation. 48 is the order of the group. Okay, so this I can write as 1 by 16. Okay, 3 by 48 is 1 by 16. Now let's look at the first operation. Is first class is the identity. Identity has character 3. Okay, so the chi of identity is 3, and whenever the identity operation acting on sigma 1 will just give me sigma 1. So I will have 3 sigma 1. Okay, next non-zero character corresponds to C2. Okay, so that has character -1. Okay, now when now C2, there are 6 operations corresponding to C2. Okay, these are the C2s. As I had said, they correspond to axes that are in between the bonds. Okay, now so what they'll do is they will transform. Now each C2 will if you look at this C2, it will transform sigma 1 to sigma 2. Okay, on the other hand, if you look at a C2 here, it will transform sigma 1 to sigma 6. If you look at a C2 here, it will transform sigma 1 to sigma 3, and so on. Okay, so the six C2 operations will so what will happen is that two of them will transform sigma 1 to sigma 2. Okay, so the two that are in this plane, so this one and the one going this way, will transform sigma 1 to sigma 2. Okay, so you have 2 sigma 2. Okay, and the remaining 4 will transform them to either sigma 3, sigma 4, sigma 5 or sigma 6. Okay, so you have plus sigma 3 plus sigma 4 plus sigma 5 plus sigma 6. Okay. It's not hard to see this, but importantly, none of them leave it as sigma 1. So all the C2 operations, since they correspond to axes that are between two axes, they will never leave sigma 1 unchanged. They'll always move sigma 1 to something else. 2 of them will move sigma 1 to sigma 2. The remaining will move it to one of the other axes. Okay, so that's as far as C2 goes. Now what about C4? So plus 1, the character of C4 is 1, and you have 6 operations again. Now the 6 operations actually correspond to C4 and C4 cube. Now so there are three C4 axes, one that is passing along each of the bonds. So this way, one along this. So this is a C4 axis. Okay, similarly this is another C4 axis, and as is this. Okay, so now you can see that sigma 1, the C4 corresponding to this axis will leave sigma 1 as it is. Okay, so 2 of them, so you have a C4 and a C4 cube corresponding to this axis. Corresponding to this axis, you have C4 and C4 cube. Both of them will leave sigma 1 as it is. Okay, so you have 2 sigma 1. Okay. Now the remaining C4s will take sigma 1 to one of these 4, one of sigma 3, sigma 5, sigma 4 and sigma 6. Okay. And no C4 operation will take sigma 1 to sigma 2. Okay. So you get okay, so that is as far as C4 goes. Okay. Next we can look at 3C2. These are C4 square. So the C4 square operation will again 2 of them. There are 3 C4 square operations. So, one corresponds to each, along each of the axis. So, one of them will leave sigma 1 as it is, the other two will take sigma 1 to sigma 2 to sigma 2. Okay, so those are the three C4. What about the inversion? Inversion will take it to sigma 2. So, then the character of inversion is minus 3. Okay, so you have plus minus 3 sigma 2 plus. Now, you have 6 S4. So, the 6 S4, the character of S4 is minus 1. Okay. And S4 operations will be very much like the C4. Okay, but then it will be C4 followed by a reflection. Okay, and so all you will get is C4 followed by a reflection. So, 2 of them will take sigma 1 to sigma 2. The remaining 4 will take them to the other 4. Okay, plus. So, this is the effect of S4. And next you have S6. S6 has character 0, so it does not matter. Then you have sigma h and sigma d. So, you have 3 sigma h and sigma d, both have character 1. The 3 sigma h, so they correspond to each of the planes containing 4 atoms. So, 2 of them will leave sigma 1 as they are. Okay. No, yeah. So there are 3 sigma h. One will leave sigma 1 as it is. The other 2 will take yeah, 2 of them will leave sigma 1 as it is, and the third one will take sigma 1 to sigma 2. So, you have 2 sigma 1 sigma 2, and then you have 6 sigma d. Sigma d corresponds to the planes bisecting the bonds. So, the planes bisecting the bonds, and there are 6 of them. Okay. Now, 4 of them will contain okay, 2 of them will contain sigma 1. Okay, so they will leave sigma 1 as it is. So, we have we have to find the effect of sigma d's, the 6 sigma d's. Okay. Now, the sigma d's corresponds to dihedral planes that are in between the various bonds. Okay. Now, 2 of them will contain sigma 1 sigma 2. Okay, and they will not affect sigma 1. So, 2 of them will take sigma 1 to sigma 1. The remaining dihedral planes will take sigma 1 to sigma 3, sigma 4, sigma 5 and sigma 6. Okay. And this completes the effect of the projection operator. We can add it all together and we can get the result. So, you have 1 by 16. Okay. Now, let us look at the coefficient of sigma 1. You have 3 plus 2 5 minus 1 4 plus 2 6 plus 2 8. So, you have 8 sigma 1. Okay. The coefficient of sigma 2 is minus 2, that is minus 4, minus 7, minus 9, minus 9 plus 1, minus 8. So, it is minus 8, minus 8 sigma 1. And then sigma 3 to sigma 6 have minus 1 plus 1, that is 0, minus 1 plus 1, that is 0. Okay. So, minus 1 plus 1, that is 0. So this is just sigma 1 minus sigma 2 by 2. Okay. So what we showed is that this projection operator takes sigma 1 to sigma 1 minus sigma 2 by 2. So, what we saw through this is that projection onto T1u, the projection operator operating on sigma 1 gives me sigma 1 minus sigma 2 by 2. Okay. And if you normalize it, okay, so you can normalize this to get normalized SALC sigma 1 minus sigma 2 by root 2. Okay. Now it's not hard to show. You can go through the same exercise, but it's very obvious from the symmetry that projection of T1u onto sigma 2 will just give me sigma 2 minus sigma 1 by root 2, okay, which is the same as earlier. Okay. So sigma 1 and sigma 2, they combine to give you, this is the symmetry adapted linear combination of sigma 1 and sigma 2, and you can easily construct the remaining, can easily construct other two orthogonal SALCs, okay, and you can show that they will be sigma 2 minus sigma 3 by root 2 and sigma 1 minus sigma 3 by root 2. Okay. So thus our three symmetry adapted linear combinations are sigma 1 minus sigma 2 by root 2, sigma 2 minus sigma 3 by root 2 and sigma 1 minus sigma 3 by root 2. Okay. And these three you can show that they form a basis for T1u. Okay. So what we have seen through this whole exercise, it seemed like a fairly tedious exercise, but it was very straightforward. Is that starting with a given set of orbitals. Okay, we started with the set that we started it was all these sigma orbitals act on the A center. Okay, on the A atom you had various sigma orbitals which corresponds to bonds with B, and we started with those 6 sigma orbitals, and our goal was to find a symmetry adapted a linear combination of these 6 sigmas which would form a basis for T1u. Okay, and those six, in order to identify them, first we found out how each of the operations acts on these sigmas. Okay, and using that we constructed our projection operator, and once we had the projection operator acting on sigma, so we took the sigma orbital and projected it onto the T1u irreducible representation, and what we saw was that we got sigma 1 minus sigma 2 by 2. Okay, and so then we know that if we take sigma 2 we will get the same thing. Okay, so if you take sigma 1 minus sigma 2 by 2 you will get itself. Okay, so that means if I take sigma 1 minus sigma 2 by 2 I should get back sigma 1 minus sigma 2 by 2, and indeed that is correct. Okay, so this was a strategy that we used, and by doing this we could easily construct that these three sigma 1 minus sigma 2 by root 2, sigma 2 minus sigma 3 by root 2 and sigma 1 minus sigma 3 by root 2, they are the symmetry adapted linear combinations. Okay, and these three linear combinations are the ones that form a basis for T1u. Okay, so far this whole exercise has shown now we have completed the discussion of how to construct symmetry adapted linear combinations for 1-dimensional, 2-dimensional and 3-dimensional irreducible representations. Okay, and we have seen how the projection operator can very elegantly work to give you these appropriate symmetry adapted linear combinations. Now these symmetry adapted linear combinations are the ones that are used to construct hybrid molecular orbitals. So when you are doing MO theory, it is these symmetry adapted linear combinations that will play an important role. Also, these are the ones that are used to find out how the various orbitals split under under the influence of various fields. So if we want to take the metal if you imagine that the A center atom is a metal atom, and it has and these B's correspond to various ligands. So then A is in what's called an octahedral field, and we want to know how the energy levels in this octahedral field split. Okay. And this can be understood, and what is the symmetry of the various resulting orbitals, that again can be understood by these basis functions. Okay. Now the next thing that we are going to do is to take this and try to do a similar exercise for a slightly different system, okay, which is a cyclic, which is the cyclopropanyl group, and we look at how the pi orbitals in this system play, how the pi orbitals in the system can be calculated. So next we will consider a cyclic system, and we'll look at pi orbitals, pi bonding. This is what is used in pi bonding, and what we want to do is to consider a system like let us say C3H3 group. Okay, so C3H3, and consider p orbitals on carbon atoms which can be used for pi bonding, and construct SALCs. Okay, so what we want to do is this group has it has 3 carbon atoms, okay, and the carbon atoms have these p orbitals. So this is a planar CH3 group, and the three orbitals, the p orbitals that are used for pi bonding, are they lie perpendicular to the plane of these 3 carbon atoms. Okay, and these are wave functions, so they have a plus and minus sign. So the sign of the wave function is opposite in the lower part. Okay, and these 3, they can combine to form pi, to show the pi bonding. And what we want to do is to construct appropriate linear combinations. So if we call this P1, P2 and P3, we want to construct appropriate SALCs to find out what are the linear combinations of these that are a basis for looking at pi bonding. Okay. Now this belongs to group this unit has symmetry of D3H. Okay, D3H has the following classes. It has identity, it has 2C3, okay, it has 3C2, okay, then it has sigma H, 2S3 and 3 sigma V. Okay. The order of the group is 12, equal to 12, okay, and it has 6 classes corresponding to 6 irreducible representations. Okay. Now P1, P2, P3, P1, P2, P3. Now the 6 irreducible representations. If you remember, we had you can show that they correspond to various one-dimensional and two-dimensional representations. Okay. Now so there will be two-dimensional and there will be 4 one-dimensional representations. Okay. Now if you look at the P1, P2, P3, they form a basis for a 3-dimensional representation that will be a reducible representation. So 3-dimensional representation, which will be reducible, is denoted by gamma, and gamma is nothing but you can work out how many times you can work out the characters of gamma, and you can show that the character of identity will be 3, character of C3 C3 will be 0, because C3 will take P1 to P1 to P3, P3 to P2 and so on. So, the character of C3 will be 0. Character of C2 will take P1 to minus P1. Okay, C2 will take P1 to minus P1. I mean one of the C2s will take P1 to minus P1. Okay, the other two will take P1 to minus P2 and P1 to minus P3. So, the trace of C2 is minus 1. Similarly, the character of sigma h will change the sign of all P1, P2 and P3. So, it will have a character of minus 3. Similarly, the character of S3 will be 0 and sigma b will be 1. And you can show that this is a combination of if you look at the character table, of D3H, okay, you can show that this reducible representation is a combination of A2 double prime and E double prime. So, A2 is a one dimensional representation, E is a two dimensional representation. So, this is 1, 2 and 1 minus 1 minus 1 0 minus 1 minus 2 1 1 0. Okay, so these are the characters of so you can easily verify that gamma is the sum of these two. So, now let us look at the one dimensional representation. Okay, let's find the projection onto the one dimensional representation, and let this operate on P1. Okay, so let's we are going to take these 3p the 3p orbitals. We are going to construct one orbital which is which transforms as the one dimensional representation A2 double prime, and we are going to construct two more orbitals which transform as E double prime, which form a basis for E double prime. Okay, so let us project P1 onto A2 double prime. Okay. So, in order to do this, we'll so it is 1 by 12. And if you work it out just like we did before, what you will get is this has P1, this does not identity keeps P1 as it is. Okay. Now, the C3s will take P1 to either to P2 or to P3. Okay. Then you have the C2s. The three C2s will take P1 to minus P1, minus P2 and minus P3. Okay. Sigma h, then you have minus 1. Sigma h will take P1 to minus P1. Okay. And then S3 corresponds to C3 followed by sigma h. So, you will get minus P2 minus P3. And then finally, the 3 sigma V's will give you, so sigma V's corresponds to these planes. So, they will give you P1 plus P2 plus P3. Okay. And if you add up all these, so you will get P1 plus P1 plus P1 plus P1. So, you get 4 P1. Then you have P2 plus P2 plus P2 plus P2. So, you have 4 P2 and you have 4 P3. Okay. And so, this is 1 by 3. Okay. So, when you project P1 onto A2 double prime, Okay, when you project P1 onto this irreducible representation, you get a linear combination of P1 plus P2 plus P3. Okay, or you just get a sum of P1 plus P1, P2 and P3, and if you want, you can normalize this by making it 1 by root 3. So, the normalized so 1 by root 3 P1 plus P2 plus P3. Okay, and you can show that P1 plus P2 plus P3 transforms exactly like A2 double prime. Okay. So what we have done is constructed a basis. We have shown that a linear combination of these transforms as A2 double prime. Now we want to find two functions which together form a basis for E double prime. E double prime is a two-dimensional representation. So you need two functions. So what are those two functions? So in order to do that, let's do P of projection onto E double prime of P1. And this you can show if you again you can see how each of these characters operates on these matrix elements, but it's not hard to show. This will just be, you'll just have a 2 here, minus 1 here, there will be a 0 here, minus 2, 1 and 0. Okay, so finally you can show that that this will give you, so it will be 1 by 12 2 P1, okay, corresponding to this. Then you have minus P2 plus P3, okay. Then you have minus 2 into minus P1, so that is plus 2 P1, and you have plus 1 into minus P2 minus P3. So minus P2 plus P3 is equal to, and so I have 4 P1 and minus 2 P2 plus P3. Okay. So I'll write this as 1 by 3 2 or so 4 by 12 1 by 6 2 P1 minus P2 minus P3. Okay, so this is a projection onto E double prime. So when the projection of P1 onto E double prime gives me this, okay, and you can show that so this is one basis function. So this is one basis function. Okay. Now we have to construct another basis function that is orthogonal to this. Okay. So to construct the second basis, let's try projection of E double prime on P2. Okay. Now if you do this, you can show that what you will get is 1 by 6 2 P2 minus P1 minus P3. Okay. So this is what you will get if you project P2 onto E double prime, you will get this. Now these two basis functions are not orthogonal. So you can show that these two are not orthogonal. Okay. So these two are not orthogonal to each other, but you can construct a second orthogonal basis function. So what we have is we have 1 by 6 2 P1 minus P2 minus P3 and 1 by 6 2 P2 minus P1 minus P3. These are not orthogonal. Okay, these are not orthogonal basis. Okay. So if you want, we can construct orthogonal basis using Gram-Schmidt procedure. Okay, so I can take any one of these and I can construct the other one using Gram-Schmidt. So, for example, you take 1 by 6 2p1 minus p2 minus p3. Okay, this has one basis function. Okay. Now, the other basis function okay, this is given by this vector, this function 1 by 6 2p2 minus p1 minus p3, and from that you subtract the projection of this onto this vector. Okay, so if you subtract the part which is the projection of this onto the first basis, you will get an orthogonal basis function. So what you will do is minus 1 by 6 2p1 minus p2 minus p3. Okay, so this is this vector, and you multiply it by a constant which corresponds to the projection of this onto this basis function. Okay, and that is not hard to work out. So what you will get is here if you look at the projection, you can calculate it. You take a dot product of these two. Okay, treat these as vectors with p1, p2, p3 as basis. So if I take a dot product, I'll get minus 2, minus 4 and plus 1. So I get minus 3 divided by 6. Okay, so I'll get minus 3 by 6, and so this you can show is just equal to so minus 3 by 6 is minus half. So I have plus half. So if I do this plus half of that, what I'll get is 1 by 6. So 2p2 minus p2, 3 by 2 p2. Okay. And then what about the p1? So I get half p1, and I take half of this. So I have p1 and I have minus p1. So those two will just cancel, and what I'll be left with is minus 3 by 2 minus and minus half. So minus 3 by 2 p2 or p3. Okay, so I can write this as 1 by 4 p2 minus p3, and if you normalize it, you get 1 by root 2 p2 minus p3, and this is orthogonal to this function, to this basis function. Okay, so this right here is one basis function and the other basis function, and you can normalize each of these if you want. So this will have a 1 by root 2. Similarly, here what you'll have is 1 by root 6 and root 6 2p1 minus p2 minus p3. Okay, so these two are the normalized basis functions for E double prime. Okay, so what we have shown is that using projection operators, we can construct symmetry adapted linear combinations for a variety of different problems. We looked at one dimensional representations, two dimensional representations, three dimensional representations, and we also looked at problems involving cyclic permutations. Okay, so like the p orbitals forming the pi system. Okay, so in fact this symmetry adapted linear combinations is one of the most used techniques in group theory, and this is an application which has found its way in both in quantum mechanics and in spectroscopy. Okay. So with this I'll conclude the group theory part of this course, and in the next class I'll change gears. It'll be the last class. So what I'll talk about is a topic that is that plays an important role in all experimental methods, that is error estimation. So I'll just spend one lecture on that, and then I'll end the course with that.